The subject of mathematical induction, about which we want to speak today, has to do with numbers. Now, of course, you know that in mathematics, we deal with many kinds of numbers. First, we learn about the whole numbers, or positive integers as we later call them. Then the fractions, or rational numbers. Still later, numbers like square root of 2, which are not rational. And some of you may even have studied about complex numbers. But our topic, mathematical induction, deals with the very simplest kind of numbers we know about, the positive integers. That is to say, the numbers 1, 2, 3, and so on. Now, if you look at the set of all of these numbers, there's one striking thing about them which distinguishes it from other sets, the kind of sets that we ordinarily encounter in our daily lives. For instance, the set of eggs in a marketplace, or the set of people in this room. The striking thing about this set is how many things there are in it. In fact, we normally say that there are infinitely many positive integers, whereas the number of eggs in a marketplace is finite, and the number of people in this room is finite. The way in which we see that there are infinitely many numbers is the fact that when we line them up, there is no last one. If you line up the people in this room, there'll be a first, a second, and finally a last one. But there is no last number. And I remember how I first discovered this fact for myself. I guess I was about 7 or 8 years old. And I was discussing with a friend of mine the important topic as to whose father was the richer. Well, he said that his father had $100. Without hardly a second thought, I said my father had $1,000, and he came back, his father had $1 million, he said. And he seemed to have me stuck, because at that age, million was the largest number we knew about. Later, I was to learn about billion and trillion, but at that time, million was the largest number. And so it seemed I would have to admit that his father was the richer. And then, in the heat of battle, I got this inspiration. All right, I said, your father has $1 million, well, mine has $1,000,001. And furthermore, however much your father has, my father has $1 more. Well, that's really the idea. That is why there is no last number. However far down you go, you can always add one more. That's why we say there are infinitely many numbers. Now, the fact that we have infinitely many numbers poses a special problem for mathematicians. Because, you see, we are often interested in showing that something is true about all numbers. And to see why the infinitude of numbers poses a problem in connection with such statements, let us contrast it with a statement about all people in this room, for instance. Suppose we are interested in investigating the question whether all people in this room are over 5 feet tall. Well, one way, in principle, that we could do this is to line up the people. First, second, third person, finally a last one, and go down the line measuring them. If we ever come to one individual who measures less than 5 feet, then we can stop the process and say at once, This sentence is false. It's not true that all people in this room are over 5 feet tall. But on the other hand, if we continue making measurements and come to the last one, and in each case find the measurement exceeds 5 feet, then we say, yes, the sentence is true. All people in this room are over 5 feet tall. But you see how important it was that we finally came to a last one. By contrast, suppose we're interested in showing something about all numbers. Of course, it doesn't make any sense to talk about a number being 5 feet tall, but consider this property of numbers. Suppose we try to express a number as a sum of squares of other numbers. For example, the number 13 can be written as 3 squared plus 2 squared, 9 plus 4. So 13 is a sum of 2 squares. We try some other number like 42. Let's see how we can express that. Well, 6 squared is 36. 4 more is 40. 1 squared plus 1 squared. Well, we've expressed 42 as a sum of 4 squares. Suppose we try a few numbers, and in each case we succeed in expressing the numbers as a sum of 4 or fewer squares. Then it would be natural to conjecture that perhaps all numbers have that property. And so we would consider the question whether all positive integers are sums of 4 or fewer squares. Well, how could we demonstrate this? One thing should be clear. We cannot demonstrate it by the method that we used in the case of the people being over 5 feet tall. We cannot line up the numbers and test them one at a time, because no matter how many we test, we will not have tested all of them. There is no last number. There will always be numbers beyond the point where we are testing. So we must devise some other method than individual tests if we want to demonstrate a sentence about numbers which has the form of a general proposition, something that is true about all numbers. Now, of course, the method that I want to talk about today is the method of mathematical induction. Before I tell you what that method is, however, I should perhaps settle in your minds the question whether this statement is or is not true. Happens that it is true. It's a question that was considered by mathematicians way back as early as the time of the Greeks. And over the centuries, quite a few well-known mathematicians had a try at proving this, but were never successful until toward the beginning of the last century, the French mathematician Lagrange succeeded in showing this. Well, we've mentioned mathematical induction several times. Let's see now what it says. Modern mathematicians prefer to formulate this as a statement about sets of numbers. Now, we've already mentioned the set of all positive integers. 1, 2, 3, and so on. Let's see some other examples of sets. Well, we might consider, for instance, the set of all even numbers. That is, the set whose members are 2, 4, 6, and so on. Or, for another example, the set of all numbers less than 5. That is, the set whose members are 1, 2, 3, and 4. Or, by contrast, the set of all numbers greater than 17, let's say. So that would contain 18, 19, 20, and all the larger numbers. Finally, we might consider the set with just the two numbers, 14 and 186. Doesn't matter. You see, we can make up sets by putting in any numbers we please. Now, among all the many sets that we could construct, there's one special kind that plays an important role in the work we're going to take up today. And that is a set that we call inductive. A set G of positive integers is called inductive, and I'll underline this word to show that we're introducing it, if whenever we pick any number from it and add 1 to this number, the resulting number is also in the set G. Well, let's take a look now at the examples of sets that we constructed a moment ago and see which ones are inductive. Well, the first one is certainly inductive. No question about it. Pick any number and add 1 to it, you get another number in the set. On the other hand, equally certainly, the next set is not inductive, because if you pick an even number and add 1 to it, you get a number which is not in the set, you get an odd number. Now this third set, you might say, is almost inductive. If you happen to pick 2, for example, and add 1 to it, sure enough, the result is in the set. Similarly, if you happen to pick up 1 to start with, or 3, and add 1, you get another number in the set. But if you pick 4 and add 1, the resulting number is not in the set. And that means that this set is not inductive. Because to be inductive, the set must have the property that anytime we pick a number out of it and add 1, the result is in the set. Well, let's look at the fourth example. Is this inductive? Well, we pick a number greater than 17 and add 1. Well, you can see that the result will still be greater than 17. So this qualifies as an inductive set. Last one is pretty surely not inductive. Now, using this notion of inductive set, we can formulate the principle of mathematical induction as follows. If we have any set, I'll emphasize any set G, and we find that, first of all, the number 1 is in G, and secondly, G is inductive, then, and this is the conclusion, then we will find that every positive integer will be in the set G. Well, there it is, the principle of mathematical induction. And now I'm sure that certain questions arise at once in your mind concerning this. The most natural question to ask is, how do we know? How do we know this is correct? That any time we find a set G which contains the number 1 and is inductive, that all integers will be in that set. But there's another question. Even if we are convinced that this is correct, we may ask, so what? What good is it? Why do we want to know about something this complicated? Well, I want to take up both of these questions with you. Let's begin with the first of them. To see that the principle of mathematical induction is correct, let's suppose that we have a set G with the properties 1 and 2, which are listed in the statement of the principle of mathematical induction. So, we are going to suppose that we have a set G with properties 1, that the number 1 is in G, and 2, that G is inductive. And I want to convince you that every number must be in this set G. Well, first off, we can certainly say that the number 1 is in G. We can say that because I am supposing that property 1 is true about our set G. But now I say also that the number 2 is in G. This is checked. I claim that 2 is in G. Now, in order to understand why this is so, we must remember first that G is inductive, and secondly, we must remember, of course, what it means for a set to be inductive. It means that whenever we pick a number out of G and add 1 to it, the resulting number is also in G. All right, we have checked that 1 is in G. Let's pick out this number 1 and add 1 to it. The resulting number must be in G, but that resulting number is 2, so that checks off that 2 is in G. And now I can continue. 3 is in G because I pick the number 2, which I know is in G, I add 1 to it, and the resulting number, 3, of course, is in G. Well, you see the point. I go on to say that 4 is in G, 5 is in G, and so on. In this way, I can show that each number in turn must be in G. Well, I think that's probably a pretty convincing argument. Most people, I think, will agree that the principle of mathematical induction must be correct, that when we have a set G with these two properties,